Subduction is a geological process that takes place at convergent boundaries of tectonic plates where one plate moves under another and is forced down into the mantle. Regions where this process occurs are known as subduction zones. Rates of subduction are typically in centimetres per year, with the average rate of convergence being approximately 2 to 8 centimetres per year along most plate boundaries. Plates include both oceanic crust and continental crust. Stable subduction zones involve the oceanic lithosphere of one plate sliding beneath the continental or oceanic lithosphere of another plate due to the higher density of the oceanic lithosphere. That is, the subducted lithosphere is always oceanic while the overriding lithosphere may or may not be oceanic. Subduction zones are sites that have a high rate of volcanism, earthquakes, and mountain building. Orogenesis, or mountain building, occurs when large pieces of material on the subducting plate are pressed into the overriding plate or when subhorizontal contraction occurs in the overriding plate. These areas are subject to many earthquakes, which are caused by the interactions between the subducting slab and the mantle, the volcanoes, and the mountain building related to island arc collisions. General description: subduction zones are sites of convective downwelling of Earth's lithosphere. Subduction zones exist at convergent plate boundaries where one plate of oceanic lithosphere converges with another plate. The descending slab, the subducting plate, is overridden by the leading edge of the other plate. The slab sinks at an angle of approximately 25 to 45 degrees to Earth's surface. This sinking is driven by the temperature difference between the subducting oceanic lithosphere and the surrounding mantle asthenosphere, as the colder oceanic lithosphere is, on average, more dense. At a depth of approximately 80 to 120 kilometers, the basalt of the oceanic crust is converted to a metamorphic rock called a clogite. At that point, the density of the oceanic crust increases and provides additional negative buoyancy. It is at subduction zones that Earth's lithosphere, oceanic crust, sedimentary layers, and some trapped water are recycled into the deep mantle. Earth is so far the only planet where subduction is known to occur. Subduction is the driving force behind plate tectonics, and without it, plate tectonics could not occur. Subduction zones dive down into the mantle beneath 55,000 kilometers of convergent plate margins, almost equal to the cumulative 60,000 kilometers of mid-ocean ridges. Subduction zones burrow deeply but are imperfectly camouflaged, and geophysics and geochemistry can be used to study them. Not surprisingly, the shallowest portions of subduction zones are known best. Subduction zones are strongly asymmetric for the first several hundred kilometers of the descent. They start to go down at oceanic trenches. The descents are marked by inclined zones of earthquakes that dip away from the trench beneath the volcanoes and extend down to the 660-kilometer discontinuity. Subduction zones are defined by the inclined array of earthquakes known as the Wild-Benioff zone after the two scientists who first identified this distinctive aspect. Subduction zone earthquakes occur at greater depths than elsewhere on Earth. Such deep earthquakes may be driven by deep phase transformations, thermal runaway, or dehydration embrittlement. The subducting basalt and sediment are normally rich in hydrous minerals and clays. Additionally, large quantities of water are introduced into cracks and fractures created as the subducting slab bends downward. During the transition from basalt to a clogite, these hydrous materials break down, producing copious quantities of water, which at such great pressure and temperature exists as a supercritical fluid. The supercritical water, which is hot and more buoyant than the surrounding rock, rises into the overlying mantle where it lowers the pressure in the mantle rock to the point of actual melting, generating magma. The magmas, in turn, rise because they are less dense than the rocks of the mantle. The mantle-derived magmas can continue to rise, ultimately to Earth's surface, resulting in a volcanic eruption. The chemical composition of the erupting lava depends upon the degree to which the mantle-derived basalt interacts with Earth's crust and/or undergoes fractional crystallization. Above subduction zones, volcanoes exist in long chains called volcanic arcs. Volcanoes that exist along arcs tend to produce dangerous eruptions because they are rich in water and tend to be extremely explosive. Krakatoa, Nevado del Ruiz, and Mount Vesuvius are all examples of arc volcanoes. Arcs are also known to be associated with precious metals such as gold, silver and copper, believed to be carried by water and concentrated in and around the host volcanoes in rock called ore. Theory on origin. Although the process of subduction as it occurs today is fairly well understood, its origin remains a matter of discussion and continuing study. Subduction initiation can occur spontaneously if denser oceanic lithosphere is able to founder and sink beneath adjacent oceanic or continental lithosphere. Alternatively, existing plate motions can induce new subduction zones by forcing oceanic lithosphere to rupture and sink into the asthenosphere. Both models can eventually yield self-sustaining subduction zones. As oceanic crust is metamorphosed at great depth and becomes denser than the surrounding mantle rocks, results from numerical models generally favor induced subduction initiation for most modern subduction zones. But other analog modeling shows the possibility of spontaneous subduction from inherent density differences between two plates at passive margins, and observations from the Isobel and Mariana subduction system are compatible with spontaneous subduction nucleation. Furthermore, subduction is likely to have spontaneously initiated at some point in Earth's history, as induced subduction nucleation requires existing plate motions, though an unorthodox proposal by A. Yin suggests that meteorite impacts may have contributed to subduction initiation on early Earth. Geophysicist Don L. Anderson has hypothesized that plate tectonics could not happen without the calcium carbonate laid down by bioforms at the edges of subduction zones. The massive weight of these sediments could be softening the underlying rocks, making them pliable enough to plunge. However, considering that some refractory minerals used for dating early Earth, such as zircon, are typically generated in subduction zones and associated with granites and pegmatites, some of these early dates may have preceded significant biological activity on Earth. Effects. Metamorphism. Volcanic activity. Volcanoes that occur above subduction zones, such as Mount St. Helens, Mount Etna and Mount Fuji, lie at approximately 100 kilometers from the trench in arcuate chains, hence the term volcanic arc. Two kinds of arcs are generally observed on Earth: island arcs that form on oceanic lithosphere, and continental arcs such as the Cascade volcanic arc that form along the coast of continents. Island arcs are produced by the subduction of oceanic lithosphere beneath another oceanic lithosphere, while continental arcs formed during subduction of oceanic lithosphere beneath a continental lithosphere. The arc magmatism occurs 100 to 200 kilometers from the trench and approximately 100 kilometers from the subducting slab. This depth of arc magma generation is the consequence of the interaction between fluids released from the subducting slab. and the arc mantle wedge that is hot enough to generate hydrous melting. Arcs produce about 25% of the total volume of magma produced each year on Earth, much less than the volume produced at mid-ocean ridges, and they contribute to the formation of new continental crust. Arc volcanism has the greatest impact on humans, because many arc volcanoes lie above sea level and erupt violently. Aerosols injected into the stratosphere during violent eruptions can cause rapid cooling of Earth's climate and affect air travel. Earthquakes and tsunamis. The strains caused by plate convergence in subduction zones cause at least 3 different types of earthquakes. Earthquakes mainly propagate in the cold subducting slab and define the wild-Benioff zone. Seismicity shows that the slab can be tracked down to the upper mantle, lower mantle boundary. 9 out of the 10 largest earthquakes to occur in the last century were subduction zone events, which includes the 1960 Great Chilean Earthquake, which at M9.5 was the largest earthquake ever recorded, the 2004 Indian Ocean earthquake and tsunami, and the 2011 Tohoku earthquake and tsunami. The subduction of cold oceanic crust into the mantle depresses the local geothermal gradient and causes a larger portion of Earth to deform in a more brittle fashion than it would in a normal geothermal gradient setting. Because earthquakes can occur only when a rock is deforming in a brittle fashion, subduction zones can cause large earthquakes. If such a quake causes rapid deformation of the seafloor, there is potential for tsunamis, such as the earthquake caused by subduction of the Indo-Australian plate under the Euro-Asian plate on December 26, 2004 that devastated the areas around the Indian Ocean. Small tremors, which cause small, non-damaging tsunamis, occur frequently. Outer-rise earthquakes occur when normal faults oceanward of the subduction zone are activated by flexure of the plate as it bends into the subduction zone. The Samoa earthquake of 2009 is an example of this type of event. Displacement of the seafloor caused by this event generated a 6-meter tsunami in nearby Samoa. Anomalously deep events are a characteristic of subduction zones, which produce the deepest quakes on the planet. Earthquakes are generally restricted to the shallow, brittle parts of the crust, generally at depths of less than 20 kilometers. However, in subduction zones, quakes occur at depths as great as 700 kilometers. These quakes define inclined zones of seismicity known as Benioff zones, after the scientists who discovered them, which trace the descending lithosphere. Seismic tomography has helped detect subducted lithosphere in regions where there are no earthquakes. Some subducted slabs seem not to be able to penetrate the major discontinuity in the mantle that lies at a depth of about 670 kilometers, whereas other subducted oceanic plates can penetrate all the way to the core mantle boundary. The great seismic discontinuities in the mantle, at 410 and 670 kilometers depth, are disrupted by the descent of cold slabs in deep subduction zones. Orogeny subducting plates can bring island arcs and sediments to convergent margins. The material often does not subduct with the rest of the plate but instead is accreted to the continent in the form of exotic terrains. They cause crustal thickening and mountain building. This accretion process is thought by many geologists to be the source of much of western North America and of the uplift that produced the Rocky Mountains. Subduction angle. Subduction typically occurs at a moderately steep angle right at the point of the convergent plate boundary. However, anomalous shallower angles of subduction are known to exist as well, some that are extremely steep. Flat slab subduction. occurs when subducting lithosphere, called a slab, subducts horizontally and nearly horizontally. The flat slab can extend for hundreds of kilometers and can even extend to over 1,000. That is abnormal, as the dense slab typically sinks at a much steeper angle directly at the subduction zone, because subduction of slabs to depth is necessary to drive subduction zone volcanism. Flat slab subduction can be invoked to explain volcanic gaps. Flat slab subduction is ongoing beneath part of the Andes, causing segmentation of the Andean volcanic belt into 4 zones. The flat slab subduction in northern Peru and Norte Chico region of Chile is believed to be the result of the subduction of 2 buoyant aseismic ridges, the Nazca Ridge and the Juan Fernandez Ridge respectively. Around Titao Peninsula, flat slab subduction is attributed to the subduction of the Chile Rise, a spreading ridge. The Laramide orogeny in the Rocky Mountains of United States is attributed to flat slab subduction. Then, a broad volcanic gap appeared at the southwestern margin of North America, and deformation occurred much farther inland. It was during this time that the basement-cored mountain ranges of Colorado, Utah, Wyoming, South Dakota, and New Mexico came into being. Steep angle subduction occurs in subduction zones where Earth's oceanic crust and lithosphere are old and thick and have therefore lost buoyancy. The steepest dipping subduction zone lies in the Mariana Trench, which is also where the oceanic crust of Jurassic Age is the oldest on Earth, exempting ophiolites. Steep angle subduction is, in contrast to flat slab subduction, associated with back arc extension of crust, making volcanic arcs and fragments of continental crust wander away from continents over geological times, leaving behind a marginal sea. Importance. Subduction zones are important for several reasons. Subduction zone physics. Sinking of the oceanic lithosphere, by contrast of density between the cold and old lithosphere and the hot asthenospheric mantle wedge, is the strongest force needed to drive plate motion and is the dominant mode of mantle convection. Subduction zone chemistry. The subducted sediments and crust dehydrate and release water-rich fluids into the overlying mantle, causing mantle melting and fractionation of elements between surface and deep mantle reservoirs, producing island arcs and continental crust. Subduction zones drag down subducted oceanic sediments, oceanic crust, and mantle lithosphere that interact with the hot asthenospheric mantle from the overriding plate to produce calcaline series melts, or deposits, and continental crust. Subduction zones have also been considered as possible disposal sites for nuclear waste, in which the action of subduction itself would carry the material into the planetary mantle, safely away from any possible influence on humanity of the surface environment. However, that method of disposal is currently banned by international agreement. Furthermore, plate subduction zones are associated with very large megathrust earthquakes, making the effects on using any specific site for disposal unpredictable and possibly adverse to the safety of long-term disposal.